conversion of classical Hamiltonian into quantum Hamiltonian, quantized Hamiltonian. So already we have derived in the previous lectures the classical Hamiltonian. And the classical Hamiltonian, we know about the classical Hamiltonian for the radiation, which is equal to this thing. H1 over 2 summation mj nu j square qj square plus pj square divided by mj. And this is the same Hamiltonian as we can derive for harmonic, for a single particle harmonic oscillator, because for a single harmonic oscillator we have only one particle. Then we can write, if we ignore the summation, then m nu x, if we replace q by x plus p divided by m. So p square divided by m. So this is the classical Hamiltonian for a single particle, but here we have summation. This is the classical Hamiltonian for the radiation. So there are many modes involved in a radiation. So we have to consider the summation for this. So this is the classical Hamiltonian that we have already derived. Now we know about the value of Qj, the operator, and the Pj operator. We know about this. So we know the Qj operator, which is equal to this, and the Pj operator, which is equal to this. Putting these two values in this equation. So here in this equation, 1 over 2 summation j mj nu j square, and putting this value. So this is square, so we can take square. Then this becomes square, and here this mj can be cancelled out with this, and this nu can be cancelled out with this. And here if we put the value of pj, then it will be square, and 1 over mj, and if we take the square of this, then 1 over iota square, and mj h cut nu j, and this can be cancelled out, and we have taken square of this. And here you can see this mj can be cancelled out with this. Then we have this h cut nu j divided by 4, because we have 2 1 2 and 2 4. And whenever we open this square, then we can get a square plus b square plus ab plus ba. So because this is very important, because here you can see the involvement of operators a and a dagger. Then it should be noted that if we take the square, this square plus this square, then multiply this with this, multiply this with this. So this is the square, this is the square. If we multiply this with this, then this exponential and this exponential will cancel out. We have this, and if we multiply this with this, so we have a dagger a. And similarly, this is iota, which is equal to this, and iota square, this is minus, and h cut nu j divided by 4, and open this square, so we have this. Now we can take this and this common, so this is a common, and we can write down all the other terms here. And also you can see that this term, this is positive, and this term as negative, so this can be cancelled out, and this a dagger square and minus a dagger square, that this be cancelled out. And finally we have this and this, so we have 2a dagger and plus 2a dagger a, and then we can take 2 common, and 2 and 4 cancel out, so we have h cut nu j divided by 2 here. And we also know that A dagger is equal to 1, and if we open this commutation relation, then A dagger minus A dagger A, which is equal to 1, and if you find out A dagger, then the value of A dagger is equal to 1 plus A dagger A. So putting the value of A dagger here, so this is the value of A dagger, which is equal to 1 plus A dagger A, and this can be added, and we can get 2A dagger A. And now if we take 2 common, then this 2 will be cancelled out with this, and this will be half. So we can get H, which is equal to summation J, H cut nu J, A dagger A plus half. And this is the quantized Hamiltonian for the harmonic oscillator. For a single particle harmonic oscillator, we can represent the Hamiltonian as H cut omega and A dagger A plus half. So this is for the single particle harmonic oscillator. But here we have H cut nu J, so there are many number of moves involved in this process. So this is the quantized Hamiltonian for the field.